Okay, hey, this is Glenn Day, and I'm going to tell you today about properties of materials. I'm using this as sort of the first technical lecture in the series for very good reason, and that's that there's a really basic skill in here that I think if you get this down, you can be an engineer, you can fake your way to being an engineer, and this will really help you tremendously in your career, and I'll tell you what that is in just a moment. First I want to go through what I want to do, talk about a little bit why properties matter. That should be a little bit implicit. Whenever we make anything, we care about what it's made out of. You know, some things feel crummy, some things crack easily, some things are really strong, and you want your cars and your airplanes to be made of things that are really strong. That's properties, things like strength, thermal conductivity, electrical conductivity. These properties matter because that's how we design things. Excuse me on that. And what I really want to say in this lecture is that first of all, properties matter. They can be measured, and that's what really separates us from the chimpanzees as we design things and we do it quantitatively. And the science works. It's beautiful, and it's really important in terms of how we go forward as a species. Even we make things, we design things based on properties. The material scientist challenge is really changing materials properties, improving them generally. It's not an easy thing to do. We can't change them by orders of magnitude, but it's been very impressive what we've done in the last 50 years. I'm going to talk about that in the next lecture. And this really leads into materials and design, and again, that'll be part of the next lecture. So the really specific goals here is I want to give you an idea of what we mean when we say properties, and I really want to talk about quantifying properties. And we're not going to say a lot about it, but we're going to give the idea that this can be done, and we can do this with electrical properties, thermal properties, electrical, optical, magnetic, corrosion, and so on. And again, that's the way we engineer everything that we use today that is really engineered. Some things are just made. The things that are engineered, we use these properties, we understand them, we make predictions. That's what makes humans great in a lot of ways. So one of the things I'm really going to harp on, hopefully through this whole sequence, although in this sequence that we're going to do it, I'm not going to say a whole lot, is the idea of units. And this is the thing that if you have this down, you're halfway to being an engineer. No kidding. I see lots of students who don't get this coming into university. It's an easy thing, and boy, can this make your life easy. You can really kind of be a genius if you just have the simple things. So let me do some really simple examples that I think you all kind of get, but if you really get your students to get this, you've done something special. Let's say you're riding your bicycle. You're pretty good. You're pretty fast. You got a pretty good bike. You can go 12 miles an hour. How long will it take you to go 30 miles? A very practical question. How long does it take you to get someplace? Will you be there by lunch? Will you be there by dinner? There's a very nice, simple way of going at this that I call the factor label method. There might be other ways. But basically, the whole idea is to solve this problem, you ask how long it's going to take. You can just look at the units. You've got to go 30 miles. Divide that by 12 miles in an hour. You can cancel out the miles here. This is on the denominator. It's on the bottom. So the denominator from the denominator goes on the top. 30 divided by 12. Gives you 2.5, and the units give you hours. So it's 2.5 hours. And that's as simple as that. You could also multiply this. We know also that there's 60 minutes in an hour. And that's another thing that you can do. Basically, 60 minutes is the same as an hour. You're multiplying by 1. Again, the denominators go away. 60 times 2.5 gives you, what is that, 120, 150. If you prefer to do it in minutes, as 150 minutes. Simple as that. It's amazing how many engineers even aren't comfortable with this all the time. Again, if you do this consistently, you're halfway home. Okay, another really practical question. You're going to go 100 miles. You have a car that gets 27 miles per gallon. Gas costs $2.86 a gallon. Changes all the time. By the time you see this, who knows what it'll cost. How much does it cost you to get there? So again, let's do it pretty much the same way. You're going to go 100 miles. MPG is miles per gallon, so I can divide by 27 miles per gallon. That's the per sign is divided. And then when you do that, you end up getting, this should take you 3.70. Well, what are the units on this? So we can cancel out the miles. Gallon is on the denominator, it goes to the top. So 3.7 gallons is what it's going to take you. What does that cost? 3.7 gallons times $2.86 per gallon equals 10.59 is what you end up getting. So $10.59 is what it costs you to get that 100 miles. So it's sounds about right? So it's about how much gas money you should charge your friends. You can do it from a nice quantitative basis. You don't have to be nasty. Just tell them, hey, did the computation, show them the computation, and you get that. Real simple thing. I call it the factor label method. I think this should be mandatory education in high schools. You can do really powerful things. And again, I say you're halfway to being an engineer if you get this right, and if you just are very careful about always getting the units. I tell you, it's amazing the problems you can solve. Okay, now let me turn this into how we actually measure this and how we get at other units. So density, this is, if you think about the units, this is usually grams per centimeter cubed, for example. This is the way we end up getting this. I should have my little erase function work. Not really. Get grams per cubic centimeter. We could also do this generally in mass per volume. And so how do we get this? Well, what we could do is we could imagine we have different chunks, and this is written up many places, and I'm sure I'll put links up to this, where we can have chunks of different sizes, big ones and small ones. What we can do is take each of these things, measure the volume. And again, the volume would be this length multiplied by that length, x times y times z gives you the volume. And again, this thing won't be in centimeters, centimeters, centimeters. So when you multiply those together, your volume comes out in centimeters times centimeters times centimeters, centimeters cubed. You can just weigh it, get the mass. So what you can do is put mass on this axis, put volume on this axis, centimeters cubed, mass is in grams. And then just take a bunch of blocks of aluminum, plot them out, and you end up getting a slope. Again, there's a lot of ways you can do this, and lots of people have developed this as a lab experiment you can do in your classroom quite nicely. And that slope is grams here, centimeters cubed here. As long as you're doing aluminum, it's going to fit on this line. This might be aluminum here. If you do steel, you're going to get something else. You're actually going to get about 3 times the slope, 3 times the density. And if you do something like polyethylene, you'll get another slope down here. For aluminum, it turns out you get a density, we usually call it rho, from aluminum is about 2.7 grams per cubic centimeter. Grams per cc is what we often call that. So again, this might be iron, this might be polyethylene down here. So that's the way I end up. So let's put a real problem in here. What's the mass of a piece of aluminum? It's 2 centimeters by 5 centimeters by 10 centimeters. So let's do the math. 2 times 5 gives you 10. 10 times 10, this is 100 centimeters cubed. What's the mass? Well, 100 centimeter cubed times 2.7 grams per centimeter cubed. Again, centimeter cubes cancel. You get 100 times 2.7, or you get 270 grams per cc. And I should be able to move backwards here. Uh, my little thing seems to be missing. There we go, it's come back. Well, this is weird. Bear with me. There we are. Or mass is equal 270 grams equals 0.27 kilograms. You might ask the question, what is that in pounds? What I can do is take 0.27 kg, multiply by 1. 1 is basically 2.2 pounds per kilogram. Kilograms cancel, and I end up getting 0.594 pounds. So that's about 6/10 of a pound of aluminum in that size. So again, it shows that we have a nice predictive science from all of this. Okay. Sorry, it's a little bit messy, but hopefully you find you can follow the basic ideas there. It's one of these things. I've been trying to work on being more orderly about these computations for a long time. It hasn't taken, maybe someday. So what I want to say is there's properties in a whole range of things. One of them is stress, which is force per area. I can take something like a wire. Wires are really nice ones. Pull on it and put some force on it, and imagine some area here. And that force divided by this normal area is what we call a tensile stress. At some stress, things break. This is something engineers use all the time to figure out if you have a cable that's big enough to carry the load, will it carry that force? Well, we know what the breaking stress is. We know what the area is. We can predict that. Strain is a percentage thing. For example, I take this and imagine it's a piece of rubber, and I now take it out and make it longer here. This is what we call a change in length, delta L. I have some initial length, L naught. My strain, we usually call it epsilon, is just delta L over L. And you can see that's dimensionless. These both have units of length, so there's no dimension on that. And that's like, for example, my strain might be, for example, in this case, imagine this is equal to 0.1 inches, this is equal to 1 inch. Then my strain would be, in that case, 0.1 over 1 equals 0.1 or 10%. So that's the way we can do mechanical properties. I can property. So these are really basic measures. How do we measure stress? How do we measure strain? We can come up with a property, which is what's the force over area at which something yields. That's something called the yield stress. That's a property. What is the force over area at which something breaks? That's a property. We can also make a stress-strain curve, which is basically a property as well, that turns into a graph where I've got stress on one axis, and this might be in pounds per square inch. And again, this would be a area unit. This might be strain, and we end up getting something that looks maybe like that. And this is a springy region. This is a recoverable region, like a rubber band, but much smaller strains. And then this is plastic deformation that we'll talk about later in the course. We can measure that in your classrooms. Strength, you basically just take something and pull on it until it breaks. Next lecturette, I'll show you something about that. We can also make a beam out of something, push it down, cause it to deform. And based on that, we can also tell you when it breaks. So again, like a breaking stress. Is basically just the force divided by the initial area, and that's something, a property, the ultimate tensile strength we talked about in the last slide. And then with this also, turns out your highest stress is down at the bottom here, and you can relate that to the length, the force, the distance into the board, and the thickness of that, and again come up with a breaking strength for that. So that's strength. It's when something breaks or fails, when it either deforms plastically or breaks into two pieces. Something you can easily measure in a classroom. You can do the same thing with stiffness. Imagine this is a rubber band. And for stiffness, what we end up doing is, imagine it looks like this. We've got stress here, and we've got strain here. And stiffness, again, is basically a slope. And I can go up this and down this in case it's a stiffness. Imagine it's a rubber band, and that stiffness on a stress-strain basis is something we call E, and that's basically a stiffness. I can do the same thing in bending. I'm not going to be as detailed about it, but again, that's that. And it's really how springy is the thing. It's not when it breaks, but it's how stiff it is. And you can imagine skis you're not going to break, but you can imagine some are really stiff, some are really compliant, and that's a material property, is that stiffness that we can come up with. And we're going to demonstrate that in the next little lecture segment. Another one you can do mechanically is hardness. Again, hardness is a ratio of force and area. This is the force you apply to something that has a shape associated with it. It makes an indent. You look down on top of that, see how much area it makes, and hardness, H, is equal to force over area, or the same as force per length squared, so pounds per square inch or newtons per square millimeter, something like that. And that's another property that we can get. Some materials are very hard, i.e. diamond. Some materials are very soft, like raisins or rubber or things like that. So it's another property you can use, and you can use this again in design. Another one that you can measure very easily is electrical resistivity. And this is actually a very easy thing to do, but you get into a lot of units. If you want to do sort of a math unit, it's a really nice thing to do. Ohm's law is what you start with. I can take a piece of wire, put a multimeter on it, and basically a meter that reads ohms, and we can talk about this, make a little unit on this. And this will tell you that this thing might be reading some number of ohms, and I could imagine I've got a wire. It has some length, has some cross-section, A, and I can find a resistance for that wire. The resistance is the resistivity, a materials property, multiplied length times area. And it turns out copper has a certain resistivity. Copper is very good conductor. Aluminum, it has about twice the resistivity, and steel has about twice the resistivity again. So you could take and make wires of the same length and diameter, for example, where you control everything to be the same, where you might have it from iron, copper, and aluminum, and a simple multimeter that you can buy for $10 at Maxter Car will allow you to measure the resistivity that way. Very easy thing to do in the classroom, and again, then you could do design challenges based on that. Thermal properties are another good one, and again, we've got units for this. Usually what we do is watts per area, length squared per time. So this is basically how much heat flows through this much area over a given time. And if you do it as a materials property, the thickness also has to factor into that. So I think it's actually, you end up with this, this thing ends up that way. So this is a resistivity, thermal resistivity of the material. Thermal conductivity is watts per length per time, and then if you make it thicker, it becomes a better insulator also. So a really good qualitative experiment you can do with this is take a block of something and put an ice cube on top of it and see how long it takes for that ice cube to melt. If you put it on a piece of copper, which is a very good thermal conductor, the ice cube will melt very fast. If, on the other hand, you put it on something that's a very good insulator, for example, polystyrene. Found my eraser button. If you put it on polystyrene, for example, that's foamed, your ice cube will sit there for a long time. That's why you make Coleman coolers out of polystyrene, not out of copper. So you can make qualitative measurements very easily with this, with an ice cube. You can make quantitative measurements with more difficulty, but the point is, if you are an engineer, you can use these units to figure out how fast the heat will go out, but that's probably beyond most high school classrooms. We can do the same thing with corrosion. Imagine you're going to make something like a bridge like this that has water over here. You got the bridge. You got these pilings here, and hanging here. But you've got these pilings that sit here in seawater. Eventually, these things might corrode, and we can come up with something where we can say that we might have this thing degrade some number of microns. It might basically dissolve at some rate, and that tells you how long the bridge is going to last. You all know, if you've seen a movie like Planet of the Apes, that eventually everything dissolves away, or lots of things dissolve away. You might be left with the Statue of Liberty, right? But the bridges are gone and all of that. But that's because rust never sleeps. Corrosion takes us away. And again, you can use units, which is a property, corrosion property, to do that. So that's my introduction to properties. The main point I want to make is properties are quantitative things you can use in design, and if you're a little bit clever, you can come up with ways of measuring it. And there's lots of ways of doing it, lots of units for this, and you can do this in your class.